The practice midterm looks similar. Some questions look similar during the midterm, right? Yeah.
I think as long as they similar, that's fine. Yeah.
It should be similar. It shouldn't be way off. So, all right. And if you were at during earlier discussion, it will be the same material. So, in case you will see redundancy. All right. Let's get started. Last week. It was last week. Happy Thanksgiving. We went over Markov and Chebyshev. I still don't know how to properly pronounce this guy's name. Chebyshev. And we also went over central limit theorem. I'm not going to cover it today. If I find out that it will be on the final, we will talk about central limit theorem during the review on Saturday. But if you have time, you can talk about it briefly. So what are they used for, Markov and Chebyshev? Can someone share? Come on, don't be shy. I'm sure one of you would like to say something. There's no wrong answer. Just say what you think they're both useful. Okay, someone who was during discussion earlier. I can wait here all day.
Are they used for moving the distribution?
I think it's I would say thank you for answering. Well, I'm trying to figure out how I can phrase it so that it is somehow moving the distribution. Okay, how about this? They are used for providing like an estimate of your probability. So let's just say one example is that you know the average is 5. For example, like any kind of distribution, you know that the average is 5. And just want to give like a rough estimate, like on the spot, like, okay, what's the probability of getting 25 based on my mean that I already have at hand. It's just used for like providing a rough estimate. We're gonna look at the difference between the two. So anyone have some thought on what they how they differ? What's the difference? Yes.
Let me think of So Chebyshev moves or produces an estimate closer to the mean, I guess, and then Markov would. I'm not too sure because based on information here, but.
Yes, you're getting there. One is providing a tighter estimate.
Yeah.
So in this case, it will be. It doesn't say here, but Chebyshev should give you like a smaller value because it's actually closer. So these are all we need. And I'll just talk about the difference. So Markov, if the random variable has to be positive, versus Chebyshev, it can be any random variable. It can be positive, could be negative. And if you know the mean, you can calculate Markov. But if you know just the mean, you can calculate Chebyshev because it relies on the standard deviation. I'll show you the formula in a bit. And okay, let's I'll write down the formula. So this will be macro. And there seems to be two variations of how it's written. So one is probability of x greater than or equals to a less than equals to mu over a. This could also be e of x over a. Well, mu and e are the same thing. And also you might see in some books or on some websites that it's actually is also alpha mu less than or equals. Can you see this? You can see it, right? Okay. 1 over alpha. Well, it's the same thing. It's just that in this case, A is alpha mu. Hello. That's Marco. And Chebyshev. That's a probability that the difference from the mean is greater than a value A is less than or equals to sigma square over alpha square A square. Or another variation is x minus mu greater than or equals to alpha sigma less than 1 over alpha square. So it's the same thing, A is just alpha sigma. So you can use either or interchangeably. Alright, so when we look at Markov, we look at the probability that your random variable is above a certain value. Whereas when you're looking at Chebyshev, you taking mean into consideration. Because that value, how far is it from the mean? You look, okay? And linearly and quadratically is here. Like if you change your R value A, you're only changing linearly. Whereas here, if you're changing your value A, it's going to increase and decrease quadratically because of degree 2. That's why the bigger the A, the more dramatic the changes will be between the two. This is abstract concept. We're going to look at example in the questions so far. Alright, here's the problem. On average, you have a website, there's 8 visits per week, and then you want to provide a rough estimate of how many people how many visits you would get in a week. What's the probability that you will get 40k visits per week? So based on the given information, what bound can we use? Markov or Chebyshev?
Markov, because you only have the mean.
Mm-hmm. Yeah. So what would your probability look like? Probability of what?
Like x equals 4,000 or greater than bigger than 4,000.
And that is less than or equals to
Yeah.
what's the expectation? What's the mean? 8 over what's 8? 40,000. 40K, and then that gives you 0.02. So that's 0.02%. What does it tell you?
The 2%?
0.02. Yeah, that 0.02. What can it tell you about your 40,000 visits?
A rough estimate of the likelihood of getting 40,000 visits per week.
Yeah, it cannot go over that. It's just a rough estimate. Because you're looking at less than or equals to.
Yeah, so if this was the Chevy, using Chevy Chef, then we would have like plus minus like in error, right? Like you can go higher or lower.
Well, you could. Mainly because. Wait. Okay, let's look at the distribution. For Markov, you're looking at the probability that your value is here. This is for Markov. Like, what's the probability that you get a value here or here? Versus Chebyshev, you're looking at x minus mu. So you wanna find. So you're looking at x plus mu and x minus mu. Like, what's the probability that things are here? The probability here is the same as probability here. Because Chebyshev, you're looking at the difference from the mean. Is it 5 from the mean, 6 from the mean?
Okay. So then what is the Markov difference?
Markov?
Oh yeah, well, the graph above.
This one?
Yeah.
You just want to see how likely are you gonna get for in this case 40,000 visits.
Okay.
Just yeah. It might be lower than that, but it's just a bound. It cannot go higher than that. All right. So same question, but now you're given standard deviation. So now let's do the bound for 28 visits for both Markov and Chebyshev. So if I were to do Markov for this one, same thing, greater than 28 visits. And then that would be less than or equals to 8 over 28. It is this is about 29%.
Question. Alpha, what exactly is alpha?
This alpha,
Yeah.
it can be any number. Let's just say you want to calculate the probability that it is greater than or equals to 5 standard deviation. So alpha is 5, sigma is the given sigma. So in this case, for example, standard deviation is 5. And then you want to calculate the probability that it's like 2 standard deviation away. So this will be 10. Versus A, also 10. So for this one, how would we write this into Chebyshev? Same question, but this is Markov, x greater than 28, 29%. What about same thing at Chebyshev? also x squared 28, but it doesn't follow the format yet. We're gonna have to tweak that. How would it look like? We need x minus mu, right? So this is equivalent to probability of x minus what is mu? Yeah, 8. So it's 8, x minus 8 less than or equals to 20. That's this right here, we're just subtracting 8 from both sides. Okay.
Is alpha's 4?
Sure. In this case, this will be 4 standard deviation. Yeah, this is 4 standard deviation. And what's the formula? It is less than or equals to this is less than or equals to sigma square over a square, right? Or in this, okay, we don't have to worry about that. We can also do 1 over. We have two options, sigma square, a square. A square in this case is 20. So this is 5 over 20 square. And then that is 6.3%. Okay. So clear. It can also be 1 over 4. Because
4 squared.
yeah. Just like how here is 1 over alpha. Sorry. Yeah, like what you said earlier, it's 4 sigma. I have to be careful there. 4 sigma, so it's 1 over 4 square. When you see this 20,
Was that equal to the 63%?
did I miscalculate that? Wait, 0.25 times 0.25. Oh yeah. This is 1 over 4, which is 0.25. 0.25 times 0.25 is 0.625. I'm just rounding it up. This is a calculation of 1 over 4 square. So it's 6.3%? Oh, yeah, 6.3%. Not 63, 6.3. My bad. Sorry. Alright, so if you estimate using Markov, you get 29%. If you estimate using Chebyshev, you get 6.3%. So this is tighter.
So our conclusion will be we pick the smaller number.
We would go with a smaller number because it's more realistic.
Can you explain why did you subtract 8?
Because in Chebyshev, we want to find how much away from the mean. In this case, it is 8 away from the mean.
And you calculated, what's that? How do you calculate A again?
So A is this number right here, 20. That's why I got 5 over 20 sigma over A. Versus if you were to, this A equals to 4 sigma, and this 4 is your alpha. So you can either do sigma over A or you can do 1 over sigma. Same thing.
Sorry, where did 4 come from?
Oh, the whole thing is 20, right? A equals 20. And then A is alpha sigma. Sigma is A over alpha. A is 20. Alpha is. Wait. I'm looking for alpha. And then sigma is 5. 20 over 5. Okay. Is everything clear? So, in part B, we can do the same thing with the 40K earlier, but using Chebyshev. So, P greater than or equals to 40K. How do you write into Chebyshev?
Subtract the mean.
Same thing, subtract 8. Is everyone done with these two? So minus 8, I'm gonna get P of x minus 8 greater than or equals to, this is 39992, less than or equals to sigma over A the whole thing square. Sigma is 5, and A is this number right here, 39992. Then that gives me n squared. This is 1.6 times 10 to the negative 6%. And again, Chebyshev is a lot smaller. And it's more realistic too, just because you have an average of 8 visits per week, but the probability of getting 40K is really, really unlikely. Rather than 0.02%, you're keeping your hopes a bit too high. It's actually really, really small. But yeah, that's the difference between Chebyshev and Markov. Questions? Alright, so this next one could be a review too. Get a bit of Markov at the end. So we have 2 dice. One is a fair dice, the other one is not. The fair dice has equal probability of 1/9 because there's 9 faces. The second dice is biased. You're more likely to get a 9 is 20%, and then the other 8 has equal probability. So calculate the expected value of the first dice and the second dice. Let's do that first. Spend like a minute or two, and then we will work on this together. 4.5?
Yeah, if this number.
That's 1 to 9.
5.
Yeah, 5. Okay, did you divide by 10 by accident? Okay, let's look on this one together. So there's 1 9 times 1, 1 9, 2.
Oh, whoops, yeah.
Okay, I'm just gonna do 1 plus 2 plus 3 plus 4 plus 5 plus 6, 7 plus 8 plus 9. I think you actually divide by 10 instead of 9. Okay. That's right. So it's 45 over 9, which is 5. Yeah, so expectation of the fair dice is 5. Did you finish part 2 yet? What did you get?
5.2.
5.2. Oh, maybe miscalculation. That's what I mean. So, let's do equal 5. So what's the probability of getting a 1 or 2, 3, 4, 5, 6? 10%. So it is 1, okay, then do 10%. 1 plus 2 plus 3 plus 4, 5, 6, oops, sorry, 7 plus 8 plus 20% is getting a 9. I got a 5.4. Did anyone else get a 5.4? You got 5.4, right? Okay, alright. So as you see here, when the dice is a fair dice, you're expecting a 5, but if you're more likely to get a 9, that number change how you expect your expectation. The expectation is a bit higher because it's trying to get closer to number 9. So that's just a review of expectation we did a while back. Alright, so part 3. You throw the first die 4 times, the second die 2 times, and sum up the outcome. What do you expect it to be?
3 years expectation.
Using the
It's 3 years, 20 plus 5.4 times 2.
How did you get 20? How did you get?
Yeah, you multiply the first expectation by 4, the second one by 2.
Yeah. So multiple ways of looking at it. So I'll get to that one next. But first, remember the linearity of expectation. This is E of x plus E of y. Does this ring a bell? Okay, yeah. But in this case, you're throwing the first die 4 times and this 2 times. Is it okay if I do 4 here and 2 here? And then that's how you get to 4 times 5 plus 2 times 5.4. That is 30.8. Is this clear? Okay, it's good. So D, you're given this one. And Y is that sum right there, getting 4, throwing the first die 4 times and the second die twice. And You want to bound that sum to at most point 10%. So what's the value of k using Markov? And remember, Markov earlier was x over greater than or equals to alpha mu greater than or equals to 1 over alpha. I'm sorry?
308.
300. How do you get 308?
0.1 is equal to the expected over A.
0.1 is. Okay, wait, say that again. 0.1
is equal to M over A. M is our expected value.
Uh-huh.
And then A is just A. Or A, sorry, K.
Hey, I'm sorry, what number am I?
So 0.1
Yes.
is equal to the expected value over K.
Uh-huh. So what's the expected value was k?
Expected value is the root of A, K is the result.
Yes, that was you.
Yeah.
Okay.
It's 0.1.
Mm-hmm. Oh yeah. 0.1.
No.
Wait.
Oh yeah.
Equals 0. Sorry. Okay. All right. Yes. 308 is the answer. One way to look at it is this is 1 over 10, right? And this k is k, and then so your alpha is 10. K equals to alpha mu. Alpha is 10. Your mu is 30.8. That's how you get 308. Yes.
Oh, I just used the other one, that's all.
The other formula works too, but yeah, this is using this formula. Okay, questions? We have a bit of time. Let's talk briefly about central limit theorem, but we're not going to go over a problem yet, just the overview. What is central limit theorem? Remember it from last lecture? That was like before Turkey. Anyone remember? Yes.
So you have any distribution, and then the sum of it or the average, either one will approach a normal distribution.
Yeah, that's right. So central limit theorem is pretty much like at the end of the day, any distribution, you sample it so many times, you will get a normal distribution. This also applies to Bayesian statistics as well. So let's just say, the same example, you CSE students. Like we have like what, 40,000 students or something, more than that, million, I don't know. This is like the population. We have a bunch of students. Each time you sample, let's just say you want to sample 10 students. Well, let's say, okay, this is like the height of UCSD student. So let's just say we have everyone's in one database. That is the population. But if we cannot only have access to a classroom or a lecture hall, we have like 100 students, for example. So if we sample once, the first time we sample, we get a mu1. The second time we sample, we get a mu2. Okay. if we sample 100 times, we get mu 100. If we were to plot this mu into a graph, we'll get a new normal distribution based off our sample. This is central limit theorem applying on statistics testing. But I don't have a problem for that just yet. If it will be on the final, we will have a problem during the review session. Okay, we have 10 minutes. Feel free to ask some questions, so you can leave early if you don't have any.
So this next lecture as well as do review.
Yeah, the next 2 lectures will be review. According to the professor, I don't know if he, I don't think there's going to be any more material, but it will most likely be review.
I didn't look at it.
On Piazza, it says the reviews are on Sunday too. Like the instructor book.
Oh shoot, did I make the wrong?
Are you sure it's Saturday?
Oh shoot. Let me double check. Oh man. Whoops, my bad. It is Sunday. It is Sunday. The post on Piazza is Sunday, right?
Yeah.
It is Sunday. I just got it is Sunday.